I don't know if you guys were able to follow up. I hope you can still see this screen as well.
Yes.
Okay, you can see my PowerPoint slide, right?
Yes, sir.
Okay,
Yes.
great. Okay, great. Thank you. So the last time I made a video on this. So if you have not watched this video, probably you could try to watch it to catch up, because I think later on today I'll also put a video on other things as well. So try to be following it up so that I wouldn't have to be repeating because of our timeline. You know, we only have 1 hour. So in that video I talk about AI. And if you follow that video, you will notice I said AI is just a way that is a technique that has evolved over a long period of time, back into the 1940s. But officially, it was a 1950 conference. That was where the name artificial intelligence was coined out. And it's nothing but a branch of computer science that has to do with creating machines that are smart. When we talk about machines that are smart, in this case, we are talking about machines that can mimic human intelligence in form of learning, reasoning, problem solving, and decision making. So, this very AI had so many other fields that are underneath it. So, one of the fields is machine learning. There is also the natural language processing, there is the computer vision, and there is robotics. So, but the most important thing that you need to know as you journey into AI is machine learning. You need to understand that machine learning is the consciousness of the AI. So it is like the brain, just like consider an AI like a full-fledged human being, but in this case, you have to consider this human being that the human have a brain. Okay, the human being has a brain. So that brain of human that helps him to reason, to be able to explain or solve problems, that's what the machine learning is the conscious part of the AI that helps it to be able to analyze all this problem. But that doesn't mean that the machine learning alone is the only part of AI. There are other rule-based methods that are not necessarily machine learning, but those ones has to do with logic. But as AI continues to evolve, it mostly stacked on that machine learning part. So when we talk about machine learning, we said it is that subset of AI that enables it to learn from data and make prediction, meaning that the machine will be explicitly programmed in such a way that it will be able to make decisions without involving human beings. Now, when we say without involving human beings, it doesn't mean humans are not in the loop. The difference is that humans have already built packages. So, in the community of AI, we build packages or algorithms. So, these packages will be built, serialized, and put in containers. And when we talk about container, it's not physical container we're talking about here. So in computer science, when I want to build a package, and I know that you are going to be using different systems. You could imagine some people are using Mac, some people are using Linux, some people are using Windows, and then there are also different versions of the software. So if I don't want it to have problem when you are downloading that particular algorithm, I will put it in a container. So putting it in a container will now help it not to be broken, so that anybody, no matter the kind of system you have, no matter the version of software you're using, you will still be able to download it and you'll be able to make your installation and it won't have any problem. So that's what we talk about when you hear with us talking about containers. And these are different. And as we progress, we'll talk more about some of these things. So these packages have been built by the community. So all what you need to do is to put your data in the right framework. So once your data is in the right framework, You will be able to install these packages, import them, and you'll be able to analyze your data set. Now, I want you to understand in the world of AI, we're talking about data. So data is the oil here. Just like in the real machines, that when you talk about automobile machines like cars, like engines, and all those things, the what power them is gasoline. It has to be probably diesel, petrol. What power your automobile cars now? They are petrols. They are all it can be diesel, it can be gas, etc. The same way in the realm of AI, what power AI is data. Do you understand? Are you all with me? So,
Yes.
what power AI is data. Good, good. So, what powers it is data. So, just like you as a human being, as a student, the more you read books, the more you learn, the more versatile you are to be able to be to perform better in your exams. The same way with AI, the more data the AI ingests, the more better the AI becomes at solving problems. So it means that any data set that the AI is not exposed to, the AI is likely going to perform very awful. So, in other words, you need to understand that AI is domain specific as well as is also general. So there is the general artificial intelligence, or we call it the GAI. But I don't want to bore you with those ones here because you have to start from the scratch before we move to these complex areas. So machine learning takes on this data explicitly without human involvement, analyzes it, and makes decisions. However, there are two parts of this machine learning. There is the supervised machine learning framework, and there is the unsupervised part of it. So, focusing on the supervised, so meaning machine learning, it takes on data, work on it, analyze it. However, there are different types of this machine learning. And it makes sense because in the real world, there are different kinds of problems. Do you understand? For example, the problems that are in Africa is peculiar to Africa. You may not find that problem in other parts of the world. The problems that are in Asia it may be peculiar to Asia, such that you may not find it in Europe. And the problems you find in Europe may be peculiar to Europe that you may not find it in Africa or Asia. So that's how the machine learning aspect also works. So there are different kinds of machine learning according to the kind of problems that people face in their daily life. So there is that supervised learning. And when we now talk about supervised, you can see from that name, supervision, it means there is some sort of supervision in the hood. Now, when we talk about this supervision in this case, is talking about labels, meaning that the machine will learn based on what you have shown it. And then after you have teach the machine or you have trained it in this case, based on some certain examples, later on you will now come and withhold a portion from the data set, and then you will tell the machine to make prediction. Then you will come back and compare what the machine has predicted with what you have withheld. Do you understand? Now, consider it like human being. When you go to a class, the teacher will teach you, let's say, mathematics, English, computer science, any other course. After teaching you and giving you all the examples in the world, the teacher will now come and tell you now you are going to prepare for tests and you are going to write an exam. Even though in Nigeria, some lecturers don't follow that format. They will not even teach you and they will come and give you a test. I have seen that kind of things before. But when we talk about an ideal condition, you are supposed to be properly taught in the class before any form of evaluation will be carried out. And it is expected that the amount of training or teaching you will receive should be much more than what you will face in exam. Do you understand? Meaning that the teaching is supposed to take about 70 to 80% of your of the input, and then the output you are supposed to be facing in your exam which you are to produce is not supposed to be condensing 20% or 10% or even 5% of everything you have been evaluated, you have been taught in the class. So there is the supervised learning, which I said it focused on teaching you based on some certain examples and withholding a portion of it and then evaluating based on what you have learned. Then under the supervised learning, we have the regression problem and we have the classification problem. Now, the regression problem, you see, in the realm of statistics, we have different data types. We have integers, which I've previously told you before. I've told you about integers. I've told you about binaries. I've also told you about categorical types. I've told you also about, in the previous class, if I'm not mistaken, I have also told you about, I told you about integers. I told you about numeric. So many, integer is also a subclass of numeric. So we have so many subtypes. However, whenever you have a data set that is not broken on the number line, meaning that it is not a discrete number. Now, when you say, for example, count 1 to 20, that's a discrete number because you are counting 1 as a whole number, 2 as a whole number, 3 as a whole number, 4 as a whole number, 5, 6, like that. So that's a whole number. But when I come and tell you 1.5, 1.57, that's a continuous number. Okay? Continuous in a sense that there are decimals that you have to approximate. So when we start dealing with continuous functions or numbers, you see us talking about ceiling function, floor functions, etc., etc. That's because these numbers are continuous on the real number line. So when you close it or you open it, so it means when we talk about closing or opening, maybe you can approximate it rounding up or you rounding down, depend on what format you are trying to look at it. So whenever you are dealing with a continuous number like height, weight, etc. For example, somebody can come to tell you you should predict stock market. When you look at stock market, it is something that is happening continuously. It's not something that you could say it's going to, you can be able to hold it on a fixation. It's something that can go up, it could come down in a split of second, it could go up again in splits of second. It's something that moves continuously. I don't know if you have seen the stock graphs. I think I did have an example of that stock I could show you on an app that I built some days back. I was just playing around during one of my spare time, and I did that app. Let me see, desktop. I could show you how it looks. So the stock market, it's always ups and down. It's ups and down. It's ups and down like that. So depend on what you're doing. But let me see if I could get the example of the. Okay, yeah, I think this will be for it. I could show you what I mean when I mean continuous. I think that would be much more better. Good. So I could come up now and open segment. Yeah, this is the file. And good. Okay. Good. Good. So let me quickly get API. Good. Okay. I think we can use this to keep. I don't want to start pulling the API. However, you could see from this example. I don't know if you can see my screen, right?
Yes, I
Good.
can. I don't know about.
Good. So can you see how this stock is moving? You can see that you see the way it moves continuously. You can see it can come up, it goes down. It comes up, it goes down. It comes up, it goes down. For example, in the month of June, this green one, which is this pineapple, it went up. However, we could see from September, it continuously went up. Then as we peak September, we started moving towards October, it went down. At the early October, it went down, and then it peaked at mid-October and started going up. So you could see the fluctuations in that stock market. It's not something that you could capture it on a time scale. It's something that is continuously moving. So that's what we mean when we talk about uh, example of stock prediction. Somebody will be interested. That person wants to know how he could best capture it. For example, nobody wants to lose. I wouldn't want to invest when these things are down. For example, in the months of February and March, you could see it was actually down. It a bit peaked in April and a bit up in March, but it wasn't up every time in March. It was on specific weeks in March that it went up. So those times that it went up, I'm interested in knowing those things, in predicting them so that I will minimize loss. So that's when we talk about continuous function. For example, somebody will want to predict housing pricing. If the person wants to know when is the best time for them to invest in, for example, mortgage. So in order for them to do that, they will put so many things into consideration, like proximity to train station, proximity to markets, maybe supermarket, proximity to the bus station, to the city center, so many other things. Uh, Um, and all that. So there are several examples, things that you cannot easily hold them on a discrete time scale. Those are what we collectively talked and said these things are nothing but a regression problem. But there is also that part that has to do with probabilistic views. For example, the probability that it's going to rain tomorrow, it's not something that I would say is a continuous problem. Rather, it is something that has to do with a yes or no, with certainties and uncertainties. So, all what I need to do is to pull out all the factors that I know. When I pull them together, I may be able to predict if it's going to rain tomorrow or it's not going to rain tomorrow. So that sort of problem is a classification problem. The same happens with when you want to detect fraud. The chances that all the transactions that happen at the ATMs, which of them would turn out to be fraudulent activity? It's also it's a rare case, but it do occur. So if you want to predict that is going to this transaction is going to be fraudulent or not, I don't know if your ATM has ever been blocked. Why now that ATM that get blocked, it is a machine learning problem. They have already trained past data set that when someone attempts to, log in the ATM several times with the wrong PIN, maybe 3 times or more than 3 times, you see that it automatically blocks it because they have already trained data set that before now hackers would likely try several pins. So when they try so many pins to get the right pin, when they run out of it, so they will just immediately put a bound. You put a sort of a threshold and say anyone that tries an account to access an account more than 3 times consecutive time, lock that account until the owner reach out to us. So that's why whenever you see that you forget your PIN and you try it more than 3 times, your ATMs or your account get blocked. until you call the bank, they get some security checks on you, then they will now open the accounts for you. The reason is because of this fraud. They are trying to detect which activity is going to be fraudulent or not. That's a classification problem. The same thing with email spam. Now, most of the time, there are some emails that you get that are not relevant. A lot of emails that are not relevant, usually they flag them up so they go to your spam. And when you check your spam mails, you will see so many irrelevant messages. So if you are not careful, you logged into those messages, you can easily get hacked by some sort of fraud people. So most of the time, Google designed this in order for them to filter out those emails that are likely to have a red flag. That something that has to do, for example, emails on dating websites, emails on someone can write you a mail and tell you and say you have won this. What you should give them your you should click on this link or something. All those kind of stuff. So that spam helps you to be able to filter these emails that are likely going to hurt you, or they are likely going to make create some sort of online profiles that by these scammers that they want to trick you into falling into their trap. So such kind of example are all classification problem. There is also the cancer diagnosis. Whenever we have this cancer, we want to check if it's going to be benign or it's going to be cancerous. So what we do is you screen it, you train the machine to recognize when it's going to be cancer and when it's not going to be cancer. So whenever it sees it in the future, it can predict and say this is cancer or this is not cancer. Then there is also another interesting part which we call the unsupervised learning problem. The unsupervised learning problem, we do not have labels for it. We just put everything into the machine and then we ask it to find patterns. So the whole case here is we are interested in grouping them based on similarities. We want to find similar objects or things that are the same, and those ones that are different from other ones. And then we also have the reinforcement learning. In the reinforcement learning, we are interested in reward. So we penalize the system when it fails and we reward it when it succeeds. So, but today, I want us to zoom into the classification problem. So at least I have been able to give you a hint about what regression is. And now let's focus more on classification problem today. So talking about classification problem, for example, if you are a fan of neural networks or deep learning, most of the time it works very nice on image data set. And then you want to train an image classifier or algorithm to recognize the difference between a cat and a dog. So what it's going to do is that it's going to divide that picture into several pixels. So those pixels that it will divide them into, it will be able to recognize what is the feature of a cat that makes it different from a dog. Then by the time it puts up all these features together, it will be able to recognize that this is a cat and it's not a dog. For example, when you look at this image that I'm showing you, you could see that these were the pixels that were extracted, for example, from the view of the cat. So by the time you put on these images together, you could be able to see that 82% shows that it is a cat. So because of the 82% that shows it is a cat, you will likely tick it and say that's a cat and not a dog. Then 15% shows it's a dog, and other percent shows it's a hat, and 1% shows it's a mug. So you will go with the 82% that shows it is a cat. So this is an image classification problem. Now, in image classification problem, you will see several things that you will be asked to work on. So there are several examples. So back to back to the training data set. So, in order for you to be able to predict that this is a cat and not a dog, you need to show the machine learning in training data set. You need to show the machine learning what is a cat and what is a dog, and what is a mug and what is a hat. So let's say this is the training data. Now, when you put in this training data, you could see you feed the machine learning with several images of a cat. You also feed the machine learning with several images of a dog. You can see you give it so many images from different viewpoints, from different directions, different colors. Then the same thing you do with the mug. You give it several images of what a mug is. Okay? You give it so many of those images, and the same thing with the image of a hat. You give him different images of what a hat is and how a hat look like. Now, by the time you do that, you will now be able to make predictions. So the training set is a set of n data points, each labeled with one of the k different classes. So it means that the training set has futures and it has a label or classes. Okay, so the training set have an example, which the example is also known as the futures, or is also known as the independent variable, depend on how you seize it. Okay, but the training set will always have the end data points or the examples. It would also have labels or classes. So just like how I remember those days when we were preparing for JAM, we have what we call past questions. So those past questions, you will study the past question, and then you would tick the answers. When you tick the answers, at the end of the day, you will go back to at the back of the past question. They will put the answers of that particular question that you are answering, and then you will now compare it with what you are guessing right or wrong. So then I noticed that when we practice, we'll go back and check the answers. We'll go back and check the answers. And I discovered something in the last jam. I only wrote jam twice. And the first time I think I wrote jam, I had a very good score. I did 218 thereabout. And then the second time I think I had like 228 thereabout. The first time I wrote my jam, I didn't know of this. So normally we would after we finish the question, we will go back and check the answer. We finish the question, we'll go back and check the answer. But I get to understand that was not a good way of me knowing those things, because at the end of the day, JAM gets to repeat some of these questions, and then I did not memorize which of them were truly the answers. So in my last JAM that I wrote 2 days to the JAM, I now discovered that why not I shade all the past questions, I shade the right answers. So if I can shade the right answers, I don't need to go and be checking back and checking. I just need to read them. So if I read them and I memorize it and I know the answer, so I discovered that approach just few days to my jam, and I did that I think for physics and another either biology or one of them. And when I entered the hall to write my jam, this thing, most of the questions were repeat. And because I have already known the answers, I don't need to start using my whole time to do the calculation all over again. I just, tick them and I moved on. So that's what the trading data point is. There will always be that answer, which is the classes. And then there will be the question, which is the futures or the independent variables or the training data points, or you can call them also the futures. For computer scientists, they will call it futures. For a statistician, they will call it independent variable, and so on and so forth. But they are all virtually the same thing. Okay. And I think it makes sense from the computer science point of view, because the futures can be millions, it can be billions, it can be so much that you can't necessarily call them independent variables. It doesn't really make sense when they become so much, and you still call them independent variables. So sometimes I do have a conflict about how the statisticians see those futures and call them independent variables. Are they really independent? And that's actually a discussion for another day. So another characteristic is learning. Remember, from the definition I gave to you, I said the ability of the machine to mimic human intelligence in form of learning, in form of solving problems, in form of decision making. So another characteristic, it will ingest the data points. It will learn from looking at the data by feeding the machine the data point. By the time you feed them, the machine will learn something. So during the training, you use the training set to learn what every one of the classes look like. So imagine I want to know the patients that are going to, or the patients that have diabetes and the patients that do not have diabetes. What I need to do is to get all the features or factors that causes diabetes in the patients that have diabetes. And then I will get the same factors for those patients that do not have diabetes. So in other words, we call it measurement. So I will measure those things. For example, biomarkers. For example, I will look at factors like their insulin level. I'm going to look at maybe other factors, their age, family history. I'll also look at risk factors such as their BMI. I'll look at also their dietary habits, etc., etc., etc. By the time I put all those, in fact, I can even go a step further by looking at their genetics. I will look at the DNA of those people that have the diabetes and those people that do not have. Then I will see which kind of genes were upregulated and which kind of genes were not regulated in those that developed the disease and those that do not have the disease. So by the time I put all these factors together, I'm going to take a portion from inside the data set. So let's say I put together 40,000 patients, participants, let's call it participants instead of patient, that in these 40,000 participants, let's say 30,000 have diabetes and 10,000 do not have. So what I need to do now is to look at all these futures, throw them into the trial by putting them in the machine. However, I'm not going to put all the 40,000. So what I'm going to do is to take a portion like 10% or 20% from the data set and say, okay, let's set aside this little percentage. And now let's see if this algorithm learns something. So by the time we feed it with the 80% of the data, the next thing we are going to do is to now evaluate it. So the evaluation phase is to predict the labels that we have withheld, in which we call the test set, because you are testing the algorithm. You are writing an exam to see if the student actually learned something or they did not learn anything. So you test the data and compare it with the true labels or the ground truths that you have held behind. Just like I told you guys on the example of JAM, that I read through the past question, I answer them, and then I go back and compare it with the original ones to see which ones I guessed right or which one I got wrong. And again, this machine learning also make me to realize that you need to train more in order for you to perform better. Because an athlete, for example, that do a lot of training are likely going to score more goals than those athletes that do not train at all. Do you understand?
Yes.
Are you with me? Do you have any questions so far?
Quite interesting, sir. Nothing for now.
Okay, good. So we evaluate the classifiers to know what they have learned, and then we will be able to make predictions. So the predictions you are making is on the new data points that you have withhold before now. Okay, so now what happened is that in order for you to be able to deploy that model into the field to solve problems for you, you will need to make sure that the data sets that are coming in real time, you will now make sure that the data conform to what you have already trained the data, the machine algorithm with. So that way, it will be able to make prediction. If you don't train make sure the data look the same like what it has seen before, you will likely run into an error. So you make prediction for new data points, you compare it with the labels that you have already withhold. So, but when you now deploy it in the field, you are likely not going to have label because, for example, imagine when you try to train a machine learning on diabetes and someone that do not have diabetes, and then you deploy it into the field by giving it to a GP. When you give it to the GP and a new patient arrived, and the GP only needs to take this measurement that you have already used to train your model. So once the GP takes those measurements and imputes them into the machine and then tap, it will make prediction. Then it will tell the GP if that person has diabetes or that person do not have diabetes. But it will make that prediction based on probability. So it will return a probability. For example, it will return 0.86, 0.89 something. Then you say, okay, looking at this probability, you know that this person is going to have. But if the probability, on the other hand, is very low, let's say 0.2, you now tell the patient that, oh, from our machine, we could see you do not have this disease. However, that does not mean it will substitute the patient from taking laboratory tests. They will still do the laboratory test and all that. But that's like a way of giving the GP an insight on the putting that patient on the right track or treatment that they're supposed to receive. For example, I wouldn't want to waste resources treating a patient on diabetes. Maybe the patient was actually suffering from a different disease. That's a waste of resources, that's a waste of time. So that particular machine learning will have helped you to solve that problem instead of start deploying so many resources and running. You don't have to, people sometimes get treated for what they are not suffering from. And that doesn't mean the machine learning is right, because there is also what we call the false positive or false negative that could also pop up at the end of the day. And we'll talk about it as we continue to go further. So in the classification problem and even the regression problem, like I told you guys, there were algorithms that have already been developed by the community that can be deployed. So a good example of such algorithms is the k-nearest neighbor, KNN. The support vector machine, SVM, the decision tree classifier, the random forest, the bagging, boosting, etc. We also have things like the deep neural networks, the deep learning and all that, but that's a different thing when we are dealing with image classification, for example. Now, talking about these k-nearest neighbors, support vector machine, decision tree, random forest, you can use them for, there are regression problems that work with these things, and there are classification problems that also work with these things. So depend on the nature of the data set that you are looking at. So what these algorithms do for you, what these k-nearest neighbor, support vector, decision tree, random forest, bagging, boosting do for you, is to help you to find patterns in the training data set that you can be able to use during prediction to know if that particular prediction falls into those patterns that the machine have seen before. And remember, during prediction, the data has no label. Okay, the data will not have label, but you already have the label. You have withheld the label. You have kept it aside, and then you will come back and compare to see what the prediction has made for you. So the prediction will be the one to output label for you or probabilities. But you already know the ground truth. But then when you now deploy it into the field, you don't have label at all. So that brings us to what we call internal validation, external validation. So during internal validation, normally you have the ground truth. But during external validation, you don't have the ground truth. Okay? Then example of unsupervised learning approaches. A good example is principal component analysis, PCA. We also have example of MDS, and we also have clustering. And I think this MDS should be talking more about factor analysis or something. But we also have several other examples, like in clustering, we have so many of them. We have so many examples of the clustering. But there is also another example that we call autoencoders. Even though it's not here, but that has to, it uses some deep neural network sort of approach, but it's also a very good approaches of unsupervised learning. Autoencoders, principal component analysis. I don't know what these two MDS mean, but we also have the clustering and all that. So when we talk about classification, let's visualize how it looks like. So let's say a good example in what I told you guys about diabetes and people that are non-diabetic, you could see, let's say this one is red, this one is blue. So what the classification does is that it tries to approximate them. Remember regression, we fit a straight line in the on the graph to try to approximate the data point. So the same way is what we do. So we kind of trying to fit in to see how this things. But in real life, we will not have this clean slate where we have we have them clearly separatable. No, it doesn't work that way in real life. You will have them likely in a very randomized way, like that. But what we should have here, we have the futures, which are the data points, and then we have the labels. Then the future decision boundaries. So these decision boundaries are what we are trying to separate them. So if we, for example, if this was to be something on emotion, you will see how it will start likely from here, and then it will move to this point and come back again and move. So until you keep going like that, until you find the point in which it minimized the boundaries, where you have some sort of overlapping, but it's not too much. You are not trying to find a perfect fit, okay? But you are trying to look for a best straight line that best approximates the problem. Okay, so that's what you're trying to look out for. So they talk about the decision boundary. They also talk about the labels. So this could, for example, be the labels and also the decision boundaries. Then you have the future. So the y-axis is normally the label, while the x-axis are normally the futures. But now, when like I told John the other day, I told him about cost of dimensionality when we have several futures. When we have several futures, we begin to have a problem, because now we begin to try to how do we fit in the problem? That's when we have a cost of dimensionality here. I did in our last class, we talked about this with him, where I told him about this cost of dimensionality. So whenever these futures increases, the chances of you finding the true value become very small. For example, when you have just two futures on the number line, you see the chances of you finding the true, approximating and finding the true value is around 0.79, which is around approximately 80%. But when you move to 3, it reduces to 0.52. When you move to 6 futures, the chances decrease even more. You have 0.08, which is just like almost 10% chances of finding the true value. When you move to 10, it further reduces. In fact, 15 futures, it becomes very small. Then not to talk of you when you have 100 futures, the probability becomes so small. You could see 1.87 times 10 raised to the power of minus 70, which is quite very, 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 very small. So the more you have the futures, the more the possibilities increases. However, remember from the beginning, I made a point. I told you that AI love data. Data is like the oil of AI. So why would so many futures become a problem if AI love data? So that's where conflict between statistics and data science, artificial intelligence starts arising from. Because statistics wants to find methodologies that will really help us to minimize effects of things like collinearities. Statistics is always struggling, to keep these futures small by working with the best futures. But AI is telling us throw everything into the tower. Let's find patterns. Okay, and again, that does not mean a bad data will give you a bad prediction model. A good data will give you a good prediction model. So you have to know that there are certain trade-offs you have to make between accuracy, between interpretability. And these things are things that when we keep going further, I will hamper on some of these issues. So statistics want us to find futures that are best in order for us to approximate this problem. For example, apple and orange mixed together, you could see them, they are quite jam-packed. So how do you put apple on one side and then you put oranges on one side? It's going to be quite difficult. If you decide to shift everything, you can put everything, you can classify them as apple, and then you leave orange out. But is that the kind of classifier you want to create? No. And what they are looking out here is the weight and the roundness. So based on the weight and the roundness, can you be able to determine if it's an apple or if it's going to be an orange? But you could see that almost these data are inseparable. However, we could also see, we cannot ignore the fact that there are so many apples or there are so many oranges that are clustered around this side compared to on this plane here. So based on those ones that are kind of here, if we find a straight line that passes through it, we could still work with it. At least we can be able to get some apples right. We can get some oranges right. But we wouldn't always get all of them right because you could see some of these ones that are here are misclassified. Now, such kind of fitted lines that help us to pass through them, there is what we call the hard classifier and also the soft classifiers. There is the soft marks and also the hard classifiers. So I still don't want to bore you. I want to keep the methodologies as simple as possible. So always know that whenever we have in the real world, we will not have a clean slate like we have here. Rather, we will be having something that will be looking like this. But however, we need to find that point, that straight line that helps us to be able to maximize the errors. So minimize the errors, sorry, and also to maximize the prediction, the accuracy. So we have a good accuracy at a minimal error. But again, it may not be easy. It may not be that easy. So sometimes you have to go back and forth, back and forth. And that's where the linear models begin to fail. Because it's not always, for example, you could see here now that the linear model would actually do a good job, but not good enough. Because there are still some apples here, some oranges here that is leaving out. There are also still some apples that are here that is not here. So we need to find a way to some sort of can I get my pen here? I wanted to draw something. Anyway, it's going to take me a whole lot of time. Okay, I wanted to see if I could get a pen. Anyway, it's fine. So I wanted to show you that it's not always that we have to use a straight line. Good. So what the future selection does is that it helps us to be able to select the best futures. Remember, we started with weight and roundness, but we discovered that weight and roundness do not give us a good future for differentiating between apple and orange. But when we go back to use shape and color, we are able to clearly separate it like day and night. Do you understand? Are you with me?
Yeah.
So,
Yes.
so
Yeah.
great. So great. So using the shape and roundness, the when we use the weight and roundness, we couldn't get a good separation. But when we use shape and color, we clearly separated it. You can see oranges on one side, apple on the other side. And truly, when you looked at the shape of apple and orange, they are not the same. Okay, they are not the same. So this kind of approaches where we try to look, we have to look out for the futures. How do we get the best futures? How do we be able to minimize this error? So we also have the nearest neighbor. So what the nearest neighbor does is that it predicts the class of new data points by majority votes of the k nearest neighbor. So it's just like what we used to say, majority carries the vote. So what it does is that in k nearest neighbor, it has this idea around similarity that ticks that are the same are likely going to be found on the same neighborhood. So looking at their neighborhood, you can be able to vote about the new class of that particular instance. So for example, you could see that the blue color, they likely group together on one side. We don't really see the blue color moving into this part of the of the shape. We see more of them concentrated on the left side, while we see a triangle, more of them concentrated on the right side. So what the new point, what the k nearest neighbor is going to do when it have a new point is to look at how close each of these is. For example, you could see that the rectangle, the square, sorry, is quite far, but the triangles are quite close to this this round shape. So because the triangles are close, it's likely going to vote among them. So when you look at this and this, it's going to say this one is likely going to fall under the triangle. So that's what the k nearest neighbor does. It weighs the ones that are close to the neighborhood, then it chooses amongst it what class it should belong to. So the problem I have with k nearest neighbor is that if I have 1 million data points, it means it will go through all of them. So it is memory intensive. That's one of my problems with it. It consumes a lot of memory because it's going to go through all the data points. It go through all of them in order to compare. So imagine when you have 1 million, is it easy for you to do the comparison among them? It's going to be crazy. So that's one of my problem with this k nearest neighbor, because when the neighborhood becomes so much, when the data points become so much, the neighborhood is going to be difficult, especially when you chooses a k value that is not that big. When you chooses, for example, a k value that is 3 or 7, and then you have million data points. Imagine cherry picking among them. It's going to be really time consuming. So memory intensive is one of the problem I noticed. So you could see when you use this I nearest neighbor approach, it finds this pattern, and of course the blue shape are grouped in one place and the red shapes are grouped in another place. Now there is also this still the k nearest neighbor. You still keep grouping them, but you could always see there is a clear separation between what falls into the blue line and what falls into the red line. Then there is also the cases where they're quite close to each other, but still we can still be able to separate it. We can be able to forego, for example, this red guy here. We could let it go by just drawing a straight line here. So when we draw this straight line, we would actually lose some point to it. Then there are also situations where we still have them very, very close, very, very close to each other, very, very close. So what we need to do again is to find a way to divide it by also letting go. We can be able to divide it. You can divide it here. You can divide it here. And there is no particular point. It's just you that will find a way, the best linear separable that you divide it. So it means you will try several values of k. So you can try 3, you can try 7, you can try 11, you can increase or decrease the number of the points. So they said the nearest neighbor properties is simple and quite good for low dimensional data. Remember what I told you, that when you have several data, it becomes a big problem because it has to go through all of them. So when you have a very few data points, it's very good in handling that kind of problem. Rough. It can create rough decision boundaries, which they call them like islands. So it's still you could be able to withdraw. Like I said, you could choose several k values. Then training complexity for n data points. So remember what I told you, that when the data points are much, it memory intensive because it has to go through all of them. Then testing complexity for m data points. So the same happens. So the error on training set, the variance and the biasness. So again, we begin to have problem with the variability on those things. How spread is these data points? How are they really, so because if we have them really chunked together, you may have problem. For example, this is where you are using k nearest neighbor of 1. So if you are using k nearest neighbor of 1, it will likely select, for example, this one is closer. This red and this blue, they are closer to each other. So it's likely going to group it that they are the same thing. Then when you increase it to 3, when you increase it to 3, it will likely take, something within this points here. It will be grouping them in 3, 3, 3, 3, 3, 3. So it will be looking at the 3 neighborhoods around that data point, and then it makes a decision. You can also increase the k to 5, like I said earlier. You can increase it to 5. It means it could look at a more bigger neighborhood. You can also increase it to 9. This depend on the kind of problems you have. So you say you get rid of the islands. If k is too large, the boundaries may become too smooth. Then lower variance but increases biasness. How do we choose the ideal k? So you also need to keep, trying to get the ideal k. So that becomes a problem because to me, I can choose k equal to 3. Somebody may come and say, no, k is not supposed to be 3. K is supposed to be 5. K is supposed to be 9. K is supposed to be 11. So the train on the training data, test on the testing data. So like I said, you do the training on the training and then you test it on the testing. So pick the k with the lowest test error. So in order for you to select the best k, again, you have to look at the errors. So the one that has the lowest error is the one you should pick. So the training data classifier, then you measure it on the testing data. Now, another way of minimizing these errors is to introduce things like cross-validation. However, I wouldn't want to bore you much about that today because I could see we have already run ahead of our time. But again, because we lose out a few minutes, that's why I jumped into it. So next time, I think I'm going to be talking about what the cross-validation is and so on and so forth. But I also wanted us to go into the practical class on classification so we could be able to do one or two things on classification.